Okay, so let's see. Okay, so let's start. Hopefully you all had a good Thanksgiving break. You're ready for the final stretch of the semester. So this is just to remind you where we are. So this is the last week of the semester. Next Tuesday we have the final. It's going to be in class, so it's a short final, just like the midterm. About the same style of exam. That's at least the current plan. Closed books. Yeah.
So the homework, if I submit it at 1 a.m.
Okay, so we got a request to extend the homework until the morning of Thursday. So it's extended until the morning, 8 a.m. on Thursday, at which time it's going to be blocked. So we're not going to give additional time because we want to give you the solutions in time for you to look at it before the exam. So that's basically it, yeah? Okay, so you should send email to me and the TAs. I think all but the 6 are graded. All the solutions are there. So if there's a problem, just send us email. Any other questions? Okay, so I want to talk about something, sort of a new section. We don't have a lot of time, but I think it's a topic that I wanted to spend some time on, and I'm going to start with asking you the question. Any? You have a suggestion? 3. There's a suggestion for 3. People agree on 3? Another suggestion? Yeah. 2? But no one said 100 or 150 or whatever. So there is something that happens here, and this is what I want to talk about. So really I want to talk about clustering. And clustering is some kind of an unsupervised learning. At least you can think about it this way. You have a collection of data points, and the goal is to find some structure in the data, organize it into sensible groups. So what exactly we are after is a little bit ill-defined, and I'm going to spend a few minutes trying to talk about this. But nevertheless, we want to be able to do it because it's a natural notion or natural way of organizing data or thinking about data. And cluster analysis is this formal study of algorithms and methods for doing it. And I want to give a really crash course on what happens in clustering, what kind of ideas are out there, and what kind of key algorithms are out there. But again, I can go back to the question. Now that you know that we are talking about clusters, you can answer maybe how many clusters are there. And no one actually wants to count the number of little points here, but rather you want to think maybe about something like this. So this is one way to do it, not the only way. And this is one of the problems with clustering. You know it when you see it, but it's not so clear how to derive something like this. So here are a few definitions of clustering. So you can think about clusters as a set of entities which are alike. under some definition of alike. You can also think about it as an aggregation of points where you have some notion of a distance, and you want that the distance between any two points in the cluster to be less than the distance between any points in the cluster and across clusters. You can also think about it as connected regions where you care more about density of points. You want to think about relatively high density of points separated from other regions by low density points. So these are, you can make them equivalent. You can think about them as different definition. But the key point is that we have some measurement space. We have some notion of distance, perhaps, or similarity between points. And while we can easily come up with a functional definition of a cluster, especially when you see it, it turns out that it's not so easy to give an operational definition and derive an algorithm that is well justified and also is doing what you want it to do. So, and the reason is that, for a given set of points might have different purposes behind it. And this will derive different way to organize it. So these are some of the underlying problems. And you can think about a lot of examples. So each one of these, so first of all, you have 4 clusters here, right? One in each corner. So this is one level of looking at it. But you can look at each one of them as a clustering problem. And if you think about, okay, so what algorithms should I use? And do I have an algorithm that does this? Or let's say does this, that might be the simplest problem. Where I'm assuming that the distance that you see on the slide, the Euclidean distance that you see on the slide, is the right distance here. This might be the easiest, but will an algorithm that works on this also work on that? And will it work on this? So hopefully you can see that the problem is not necessarily just distances, relative distances, not even density, but rather very, very different types of issues can come up depending on the way you think about the data point. And once you have algorithms for each one of these 4, you can think about this. How many clusters do you see here? So you definitely want to split this to 2, if you want to split it at all. But clearly there are difficulties, right? So there are points that are very, very close together that you want to place in 2 different clusters. And the reason you want to do it this way is a global reason, right? It's not a local reason of distances between points and so on. So if here, maybe you can think about some local algorithms, hopefully it's clear that here and here, you have to think a little bit more than on local algorithms. And these are some of the difficulties that come up when people think about clusters. Yeah? I don't know. I mean, maybe. I mean, the problem is not solved in any way. And what I'm going to try to do is give you some ideas that people have used, but it could be that there are other algorithms. I don't think it's as simple as that, because the notion of distance is important here, and you won't get it for free. I mean, maybe you'll embed it somehow, but still, the way to embed it is going to require knowing something. So one perspective is that clustering is actually not a learning problem. I don't need to talk about it in this class. It's really an optimization problem, right? So what we have is a set of points. Let's say that we have some pairwise distance between points. And the goal is to devise an algorithm that splits the data so that it optimizes some natural conditions. One thing that I want to mention now, given that you have this in mind still, is that we're always going to talk about pairwise distance. You will see later today that even though we talk about pairwise distance, this does not necessarily dictate everything, because we'll have to talk about some derived distances and some algorithmic issues that can take a given distance and do different things with it. But there is a natural notion, or at least we feel that talking about distance between points is a natural thing. The question is, what would be this natural condition that we want our optimization to achieve? And people have thought about it for a long time, and here is a list of some conditions. And let's see if you agree that they are natural. So here is one. We want self-invariance. By self-invariance, I mean that if you have some distance function d, and you derive a partition of the data using this d, when you multiply d by some constant, you will get the same partition of the data. Seems natural, right? Basically, it's some kind of scalability. If I blow up everything by 7, it shouldn't change the way I partition the data. 2, richness. So basically, this says that the range of my algorithm is equal to the set of all partitions of S. A little bit more carefully, really richness requires that for any partition gamma of the data, I should be able to construct some distance function such that clustering with my algorithm F according to this distance function is going to give me this partition. Right? So I can do whatever I want with the data. That's kind of the richness requirement. I can partition it any way I want. And then there is a consistency assumption or a condition. And I'm going to just basically, the way you think about it, if you have a partition, gamma, you can think about gamma transformation of the distance metric. Essentially, what it's going to do is that if you have some partition that you got with distance metric d, and you reduce the distance within clusters and increase the distances between clusters, and you get a new distance metric, d prime, this way, the partitioning is not going to change. Again, what I'm saying is this. Let's assume there is some metric d that gave me some partition. I'm inventing a new partition, a new metric, d prime, such that distances that are inside clusters shrink, and distances that are across clusters grow. You hope that the algorithm is such that you don't change the partition. Yeah? I don't see the relation here. So VC dimension we define for a Boolean function, right? So here is a set of points, and I want to partition it to 2 types of points, positive and negative, say, right? And then we define an expressivity, which means that we did not allow all partitions. This is actually good to bring VC dimension back to the top of your head. So we talked about positive and negative points. In principle, there are many ways to partition a given set of m points. And we said that if we are going to partition it with a specific class of functions, say intervals on the line, all our points are on the line, then we cannot get all partitions, right? By partition, I mean I cannot just take any random subset of the points, say this is positive, and the rest are negative, because I'm restricted with the family of functions that I'm using to partition. But here, different ball game. When I say partition here, it's a different type of partition. There's no notion of labels, for example, right? I'm just partitioning it to groups, and I didn't even tell you how many groups. So I'm assuming a fixed number of groups here. Okay, so everyone agrees that these are kind of natural conditions, hopefully. Maybe some more natural than others. You know, if I had to vote, I would say that the first and the third are definitely things that I want my clustering algorithm to satisfy, and maybe I'd be willing to give up on that or relax the second one. But either way, these are natural conditions. The problem with this is this theorem, that it turns out that there is no algorithm that satisfy all three conditions. So mathematically, it's a very nice theorem, right? Because it says, here are three natural conditions. You cannot come up with a theory that satisfies it. So this basically tells us, you know, okay, maybe we won't have a consistent theory of clustering. By the way, there are some other theoretical results that try to relax this and, you know, think about relaxing some of the conditions different ways. I don't want to get into it. I just want to use it as a motivation to the fact that really what is happening in clustering is we develop different heuristics methods that make sense. And they will not satisfy everything that we wanted to satisfy. And that's life. So, and in fact, we can develop these heuristics from different perspectives. We can develop them from probabilistic perspective or others. And I'll give some examples. Now, one important thing to keep in mind when we think about developing heuristics is that a key component is this measurement space. So we have to think about what are reasonable distance or similarity metrics. I'm going to use distance and similarity interchangeably, even though they are the inverse of one another. And you can also think about what are the important dimensions of the data. Right? So you place a point in some space. Maybe some of the dimensions in this space are more important than others. And as a function of these two questions, we're going to discuss clustering methods. I'm going to hint that there exist also methods for learning distances, but I'm not going to talk about it. And there are dimensionality reduction methods that address what are the important dimensions of the data. I'm not going to get to talk about it. So I'm just going to talk about different ways to think about clustering and different clustering algorithms that come up as a function of it. Okay, so just to make things a little bit formal, we have m data points. Each data point is assumed to be a d-dimensional point. And in general, in most cases, we won't make any statistical assumptions of the data, nor the number of clusters, but specific algorithms will make assumptions. So given a specific algorithm, they will probably say, let's assume that I want to cluster it into k clusters and go from there. Okay, so we're going to have a distance measure. And so essentially, you can think about the input to the problem as a matrix with where the ij cell is the distance between the ith data point and the jth data point. That's really the input that we have. And this is where we're starting. Now, of course, there are many, many distance metrics. You all saw definitions for distance metrics, and these are the definitions that you've seen. You've seen metric as a function from RD cross RD to R that satisfies these three conditions, right? It's non-negative, it's symmetric, it satisfies the triangle inequality. It turns out that in most of the literature in clustering, even though we call something a distance metric, it's often not a distance metric. In many cases, it will not satisfy triangle inequality because applications behave differently, and in many cases, it will not be symmetric just because the application will require it not to be symmetric or will not require it to be symmetric. Examples. So again, there are many, many things that people have used as distance metric, depending on the space and the application. Of course, if you work in discrete space, maybe you'll invent some other similarity metrics. I'm just pointing out a few metrics, both because you've seen them before and because I want to make a point using it. So you've all seen Euclidean distance, Manhattan distance, which you can think about L1, this is L2, and L infinity, which is the max distance over all coordinates between x and y. And here's an example of something that people often use, d square, where d is the Euclidean metric, but it's not a metric. Okay, so here are some examples, right? So I'm looking at these 2 points, and I'm measuring the distance between them using these 3 distances. Again, this is something that you've seen and should be easy. The reason I want to mention it is the following example. So if you look at these 2 red points, I call them A and B here, and I'm looking at L infinity, it's 5, right? Because along this axis, the distance between the red points is 5. L2 between them is a little bit more than 5, right? Because I shifted one from the other on the x-axis. So it's a little bit longer, more than 5. Look at the green points. I call them CD here. Along the y-axis here, the distance is 4. So L infinity is going to be 4. L2 here is going to be square root of 4 square plus 4 square, which is something like this. And the point that I wanted to make is, in L infinity, C and D are closer than A and B. In L2, C and D are farther than A and B. So distance metrics do not necessarily behave the way you want, right? So the relative positions of points, the relative order of points is going to vary with the distance. This is something to keep in mind. So distance actually matters, right? Okay. So now that we know that clustering may be sensitive to similarity measures or distance measures, just given the example that I've given, we can think about, can we get around this by inventing more sophisticated distance metrics? And you can do some, but you cannot do all. So you can devise distance measures that are invariant to some transformation that you care about. So for example, if you care about shift and scale invariance, right? So you don't want moving all the points or blowing up all the points by a constant to bother you, you can devise a distance metric that can tolerate that. And you do this. This is something that is called Mahalanobis distance. And essentially, you take the L2 and put a matrix here, the covariance matrix of the data, and this is going to take care of shift and scale. This is just the definition of the matrix sigma that I'm putting here. Again, something that you've seen in some context, perhaps didn't think about it from the context of, dealing with large set of points and clustering them. And you can do other transformations. So if you care about rotations, then you can devise a distance metric that will be rotation invariance by rotating the axes so that they coincide with the eigenvectors of the covariance matrix. And this is a transformation that is called the principal component transformation. Again, I don't want to get into the distance, just understanding that you'll have to deal with distances, and you have to understand that there are some limitations, and some of these limitations can be addressed under some conditions. Okay, still talking about distance, so we define pairwise distances between points. Often you want to care about distances not only between points, but rather between sets or between points and sets. And there are natural ways of doing it, right? So this is a natural way to define a distance between a point X and a set A. You basically average over the set A the distances between X and Y, where Y ranges on A. Similarly, you can define a distance between two sets, A and B, right? So you'll take all pairs, you'll average it over this size A times size B, which is the number of all pairs. We will see that there are other ways of doing it in a few minutes, and it turns out that a lot of the algorithms actually vary not by the basic D, but rather by how do we make this basic D between points to a distance between sets of points. Okay, so now that we have all the tools, we can define an algorithm. And if you were given the task of inventing a clustering algorithm, I think this would be maybe the first clustering algorithm that you'll come up with. And you'll see that it's very simple and very natural. So just notation-wise, so we have a set of endpoints. We have a distance that is given to us. I'm going to use some threshold T. Ci will represent clusters. Z will be a representative of the cluster. So one of the points that I call the representative of the clusters. And I, in the following algorithm, will index into data points. J will index into the clusters. Okay, so basically that's what I have, right? So I have a collection of points. And my question is really, given a data point I, which cluster do I put it in? That's the basic step in the algorithm. And this is what we're going to do. So we're going to initialize the cluster using the first point, the first cluster. My K, which is the number of clusters now, is 1. And sequentially, for all data points, what I'm going to do is I'm going to compute the distance from the ith point to all the clusters, right? I'm doing it by computing the distance to this representative of the cluster. And then I'm going to minimize over all j's, over all clusters, and phi di, which di is going to be the best distance from the ith point to any of the clusters. So basically what I'm doing here is I'm assigning a cluster to the point I. Once I do this, I ask the question, is it close enough? Is di, which is the shortest distance from xi to any of the clusters, is it short enough? If it's short enough, below a threshold, I say, okay, I'm going to put it in that cluster. Otherwise, I'm inventing a new cluster. And that's it. That's an algorithm that once I finish running over all the examples is going to give me a partition of the data into clusters. Clear? Very simple. Yeah. That's the algorithm. You can invent other algorithms, and maybe you can invent even better algorithms. We will try to do it later. But for now, that's the algorithm. And your question raises one limitation of this algorithm. So what's the key limitation of the algorithm? Say it again? Points are not reassessed. Or in general, you can say it depends on the order. Right? So if I've seen it in one order, I'm going to cluster one way. If I permute the points, I'm going to cluster it another way. So clearly, it's not the best algorithm, but it gives you an idea of here's a clustering algorithm. And immediately, you can come up with some improvements. And you probably don't want to use this algorithm as is. I just wanted to give a simple example that shows clustering is not as scary. You can write your own. And when you try to think about how to improve it, one of the key things that is becoming important, and you'll immediately think about it, is this conflict that you have between what I call here association and dissociations. So really, if you want to define some goal, you want to have some measure of similarity within a group of points, within a cluster, and some measure of similarity between groups. And of course, what you want is you want the within similarity to be maximized and the across or between similarity to be minimized. And you want to do this at the same time. Right? This is a clear desiderata of a clustering algorithm. It turns out that all the standard algorithms that you can think about, including the one that we just went through, and heuristics improvement that you'll come up with, do not satisfy both of them at the same time. So it turns out not to be so easy to do it. And you can think about this as an example, because here you're bound to do something more than just kind of this local thing. So in order to think about it, I'm going to define something. I'm going to define what I call here a scatter measure, which is a within cluster measure. Essentially, it's the average distance from a point to its representative. Right? So you already have a cluster. The cluster is Cj, and this is a metric. This is a measure, of how tight the cluster is. Right? So I'm basically averaging over all the jth cluster the distances from xi to the representative. Once I have this, I can also define the quality of the cluster. You can think about this metric as a measure for the quality of the cluster. So what do I do here? So here I'm running on all the data points. For each point, I'm finding the closest representative, and I'm averaging it. Right? So here I don't have a notion of a cluster. Now, of course, you can put these two together and think about what will be the best global clustering scatter. The best global clustering scatter will be when xi is in the right cluster, in the cluster that is represented by the closest representative to xi. And you can do this math. I'm not going to do it here. It's here. You can go over it. I want to move on to give an algorithm that actually uses these metrics, these measures that I just defined. It's going to be a better algorithm than the one we started with, and in fact, it's going to be an algorithm that you've seen before. It's called k-means. So in this case, I'm going to fix k. I'm not going to change it as we go, just like in the previous very simple algorithm. And here is how the algorithm is going to go. I'm going to initialize centers randomly. So I know that I have k clusters. I'm choosing k centers randomly. This is my first round. And then I'm clustering using nearest neighbor. That is, I'm placing xi into the jth cluster if j is the argmin of the distance between xi and zj over the j's. Okay, so basically, I'm placing it in the cluster whose representative is closest to xi, right? Very natural step. Now that I have this, I'm choosing new centers. How do I do it? I'm choosing zi to minimize the di that I defined before. Right? So basically, I have a cluster. I have a lot of points. I have this measure, scatter measure that I defined. This scatter measure assumes that I have a center Zj and gives me a distance or a measure for how tight this cluster is. Right? Now, different centers that I'm choosing are going to give me different tightness measures, right? So in the algorithm, once I have a cluster, I'm replacing or I'm choosing a representative so that this metric is minimized. So this is the choose new centers algorithm. Once I've chosen it, I can compute the quality of the cluster using, again, the D metric that I defined before. It's the D metric that corresponds to the rth round. And then I check, should I continue or not? You can check whether you want to continue or not different ways. Here I'm checking it. My stopping criteria is a relative stopping criteria. I'm looking at the improvement in the relative improvement in the quality of the clustering, right? So dr minus 1 minus dr divided by dr minus 1. And I want to compare this to some threshold. If I'm not happy with this ratio, I can continue. I'm going back to 2. So now, again, I have a new set of representatives. I'm clustering, choosing a new set of representatives, and I can keep on going. So is the algorithm clear? Yeah. Okay, very good question. So computationally, you can immediately see that this is the hardest step here, right? Because in principle, the way I do it is I have to go back to my definition here, dj, right? And I say, well, every zj that I choose gives me a number here. Choose the zj that gives me the smallest number here. You can try all options. This would be one possibility. Perhaps, in some cases, you can do it more efficiently. We'll get to it in a second. But in principle, I need to try. Okay. That's again, the way I've written it here, I'm choosing one of the points in the center, as a center. And indeed, this is going to be one of the key things that I may want to change in this algorithm. But first of all, I want to make sure that the algorithm is clear and that you know that you've seen it before. Right? So really, this algorithm is EM. But it's a hard EM because if you go back to the lecture that we called K-means in the EM lecture, the difference was that for a given point, we did not choose a cluster to place it in, but rather we had a distribution over all K clusters. So a piece of the point xi went to cluster 1, another piece of it went to cluster 2, and so on. Right? And they sum to 1, these pieces. That's the only difference. So here, in this step, I'm choosing new centers. So for each, I'm taking xi and placing it in Cj. I'm just deciding which is the Cj, rather than saying, a third of you is going to go to this cluster, and a third of you is going to go to another one, and so on. That's the key difference. So this is what we call a hard EM algorithm, rather than a soft EM or the standard EM. Another thing is, the question that you've raised. There are several issues that come up here. One of them is, why did I insist that the center is an element in the set? In principle, you could imagine that the center is a virtual element, not necessarily one of my data points, and it's there just because I need a center. I need some pivot to do the computation around. And in fact, if you use Euclidean distance, you can achieve the minimization stage that you want directly. I don't need to try all options, but rather I can just compute average. It's going to be the minimal relative to the Euclidean metric, but it will not be a data in the set. It will be a virtual element. And different metrics that you will invent will give you these advantages also, right? So you'll be able to compute a center, a representative, either a representative or a center, depending on whether you insist that it will be in the set or not, in a more efficient way than just trying all options. So this is really an important issue in k-means, because this is where the time goes. Depending on your metric, you will or you will not be able to do this efficiently. But other than that, it's a very good clustering algorithm. So there's huge literature on clustering. And I would say that, you know, with almost no exceptions, try k-means. It's going to work, and it's going to work well. And just like in classification, where we talked about a lot of different learning algorithms that at the end we show they're very, very similar to each other. And the key difficulty and the significance comes from which features space you work in. The same is going to happen here. You know, it's going to be a lot more significant to find good metrics than to play with different algorithms. K-means is going to do the job in many, many cases. But we have more time for today, so we're going to talk about other interesting algorithms. Of course, there's an issue of what is K. And you can think about it different ways. There are several algorithms. The simplest approach, of course, would be to try different values and measure the quality of the clustering, this D that we define. I have here a few slides here that talk about algorithms that do it, but I don't want to spend time on it. I want to go back to other approaches to clustering. So, of course, one of the issues is that you can see from this nice collection of clustering problems is that no single distance metric is going to do it. And probably no single clustering algorithm will do it. It will have to depend a little bit on what you know about the data and so on. And one of the key things is to really understand what's happening here. So the advantage of k-means is that it's a principled algorithm. We know that it makes an assumption, a probabilistic assumption on the data. It's really an EM algorithm. The way we showed it in class was we assume a mixture of Gaussians. You can assume a mixture of other things, and the algorithm is going to, the update rules are going to be developed in exactly the same way. So you have some principles behind this algorithm. The question is, can you develop principled algorithms under other assumptions or for other algorithms? Or are we bound to think about clustering as a bunch of hacks or heuristics? And it turns out that you can say a few interesting things. And again, I'm not going to be able to give details, but I want to show you some interesting things. So one family of algorithms is called agglomerative clustering. Essentially, agglomerative clustering is a very, very simple algorithm that starts, as usual, with a pairwise distance. And then it defines as a function of D, lowercase d, and uppercase d, which is distance metric between sets, between clusters. Once we have defined this uppercase d, we have an algorithm. The algorithm says, well, initialize by placing each point in a separate cluster, and then start combining. Very different algorithm than the one we started with, right? But also a very natural algorithm, right? So at each stage, merge the two closest clusters according to capital D. Okay? Now, hopefully it's clear that even if you fix this d, lowercase d, changing capital D will make big differences. And indeed, different definitions of D are going to give rise to radically different partitions of the data. What's interesting about this is, and the reason I mention it here, is that it's possible to think about generative models that justify different definitions of capital D and analyze the algorithms this way. So again, I'm not going to give the details, I'm just going to give some ideas. So here is one natural way to define capital D. It's called single link clustering. And essentially what we're doing is, given that we have two clusters, we are defining the distance between them as the minimum dx1, x2, where x1 is in C1, x2 is in C2. Make sense? In the case of these two data sets, if you think about it, this is the clustering that you will get, which is what you want to get, right? So you have two kind of lines of data, and the distances between points in each line are smaller than the distance between the lines. Single link is going to do it. You can also define complete link clustering, which defines it as a maximum, not such a natural metric, I would think. But there are other metrics that are very natural. So we can think about this, group average clustering, where you look at the average distance between groups. You can define what is called Ward's method, which looks complicated here, but this is some kind of variance of the data. And all these, the interesting thing is that if you think about it, even for this data set, they're going to give you different ways of partitioning the data. I have here some analysis, which I'm not going to go through, that will give you some ideas of the fact that it's possible to define generative models around this. So basically, these are heuristics, or invented as heuristics, and then people try to give them some probabilistic interpretations by devising generative models that give rise to these metrics. Yes? Okay. That's a good question. Yes. So a lot of the literature on clustering deals only with splitting to two clusters. Not k-means, of course, because there the k, you assume it, but it doesn't matter later on. We're going to get to it, to another family of clustering algorithms, where the assumption is, if you know how to do it, how to split it to two, you can do whatever you want, because you're going to recursively call the algorithm. You can disagree with this, because sometimes maybe if you recursively call the algorithm, you don't get exactly the same results as if you decide to split it ahead of time to k clusters. But that's a standard way of using clustering. OK, so the bottom line of what I said so far is I want to bring up to your attention the following interesting interaction that exists between the metric and the clustering. So let's look at these three data sets here. Let's first look at the two data sets on your left. So I'm defining the Euclidean metric. So I have two features. We are in the plane. F1 and F2 are my features, X and Y if you want. And this is the Euclidean distance. Now, with the Euclidean distance, I can think about two algorithms. I can think about the single linkage algorithm that I just discussed before, where I'm doing agglomerative clustering. I'm assuming here that the distances along each line are a little bit smaller than the distances, the orthogonal perpendicular distance between these lines. And therefore, single link is going to give me this clustering, black points here, white points here. On the other hand, if I'm using k-means, k equal 2, with the same distance metric, I'm going to get this partitioning. So the same distance metric, different algorithms, different results. On the other hand, let's now look at the two data sets on your right. And in both cases, we're going to use the same algorithm, k-means. In one case, as I said before, I'm using k-means with the Euclidean L2 metric. Here, I'm going to use k-means with a linear metric. This is the metric, right? Basically, L1, absolute value distance of the features, sum over all features. If you think about it, here, k-means is going to give me this split. What is the point? The point is that the algorithm and the distance metric really interact. You cannot talk about one without talking about the other. You cannot say I'm going to use k-means. Doesn't matter what the metric is. It's going to give me the same result. It won't. And you can also not say I'm going to use this distance metric. It doesn't matter which algorithm I'm going to use. So these two interact a lot. And therefore, it's important to think about it. You know, there's really no universal metric and no universal algorithm, and these two interact. And if you're in the business of trying to learn a metric, it's important which algorithm you're using as a building block inside your learning algorithm. Okay, so that's one important lesson. The second, and just to summarize, in the course of doing this, we talked about three different algorithms. We talked about a very basic natural algorithm that had no limitation. You know, it generated clusters as needed on the fly, but it had some problems with sensitivity to order, you know, one time running on the data, and so on. So it's not an algorithm that you want to use as is, at least. And then we talked about two families of algorithms that are really important. One of them is agglomerative learning algorithm, clustering algorithms. And the second one, k-means algorithm. So now I want to move to another family of clustering algorithm, which I call here graph algorithms. So graph theoretic methods are very natural when we talk about clustering. You can always think about your set of points as nodes in a graph. Edges are drawn between pairs of nodes, where if you know the distance between pair of nodes, you put a weight on this edge. You can either do distance or similarity. I'm going to use more similarity in this part. And basically, this is your input to the problem, or this is your input with some numbers on the edges. That's the problem. And again, it's very easy to think about algorithms to deal with it. Really, our goal is to partition the graph, or the set of vertices of the graph, into, at least here, a disjoint set of vertices, where again I have some measure of similarity among vertices in each partition and across partitions. And I want the similarity within a cluster to be high and the similarity across to be low. So again, the question is, what's a good definition? And as before, it's hard to come up with algorithms that do both things you want, sort of minimize, maximize similarity within and minimize similarity across at the same time. But again, you can really think about very simple algorithms that will decompose the graph into connected components. So here is the simplest algorithm that you will probably come up with. You can start by taking your data and constructing a maximum spanning tree. Right? So I'm working with similarity. So now I have a tree. And then in order to generate connected components, I'm going to drop the weak edges, or what I call here inconsistent edges, from this tree, and I'm going to get connected components. Of course, the question is, how do I define these inconsistent edges? You can use a threshold. You can be a little bit more sophisticated and be sensitive to the neighborhood. So, for example, you can delete an edge if its weight is significantly lower than that of nearby edges. And you can invent something that is more application-specific. Yeah? It's minimum because I'm thinking about, let's see. No, I'm not doing any cuts at this point. I'm just doing MSTs. It depends whether I talk about similarity or distance. If I talk about similarity, it's maximum spanning tree, yeah. So I think that in this part, I always talk about similarity. Okay, but in any case, the point, so again, the algorithm is very simple. You can derive it yourself. The key point that I want to make here is that all these methods are local, right? So really you think about pairs of points, and therefore they're not very different. I mean, they just, you can think about them as, you know, you can write them differently, but they're not very different from the method distance-based method that we discussed before, just a different representation. And also in this domain, you can come up with very, very similar method. You can come up with a agglomerative method here, which basically say that you're going to start with each point in its own cluster, and then you collect them. You can go the other direction. You can come up with divisive algorithm, where you start with all points in one cluster, and then you split them. So again, these are natural algorithms. But all of them, and I'm going to skip this because it's uninteresting, all these are local algorithms. And if you think about problems like this, local algorithms are not going to do it here. This has to be clear. You really have to be able to think a little bit about, or to have your algorithm think a little bit about some global properties of the graph. And this is where if we want to think about graphs, it brings some ideas of how can we partition a graph into disjoint set by thinking about global properties, something that takes into account more than 2 points when it makes a decision. So this comes up in a lot of applications. I think the algorithm that I'm going to describe now came up in the context of image segmentation, where you have an image and you want to split it into regions that are coherent in some sense, you know, some background, some chairs, some tables, walls, and so on. And these are regions that are coherent but they form clusters of points. And clearly in this case, global properties are important, because if you just look locally at regions, it's not clear that the clustering that you'll get will satisfy what you naturally see. Here's another example. Here's a bigger example of the same thing, where, again, global properties are important here. So the question is, how do we do it? And the key idea that was just mentioned here is to try to define some global degree of similarity between parts of graphs. And you all know what would be a natural measure for this. What would it be? Cut. So a notion of a cut in a graph is a global measure. And this is how it's defined. So given a graph, we partition it into two disjoint sets A and B, and we're going to measure the degree of similarity between the two parts this way, basically as the sum of the weights of those edges that connect nodes from A to nodes from B. So I'm summing overall U in A, V in B, the distance between them. So that's a global metric that looks at these two parts. And you can say that the optimal bipartition of G, or partition of G into two parts is the one that minimizes this cut value. And there are algorithms that can compute this efficiently, so we're not going to think about computation at this point, just about this notion of a cut. So those of you that have played with cuts, and this actually, again, answers the question that you asked before about how to deal with k-partitions. The way it's being done is by applying this recursively. And as I said, there are downsides also for doing it, and there are other ways. Yeah? Right. Okay, so that's exactly the downside. So it seems like a very nice idea in the abstract, but when you get to do it, it's true. You will not get what you want. Really, if you look at these two data sets, where it's clear, I think, where we want to split it, if you minimize the cut, you will get this. Or maybe this. Basically, a cut as is will basically, its value is going to increase with the number of edges going across the partition, and therefore you'll choose one point in order to minimize it. And it's not what you want. You want this. So the question is how to still use the idea of a global metric, global measures for partitioning graphs, and avoid this kind of thing. And the solution is going to be to normalize. We're going to normalize the cuts. And the way we're going to normalize is we're going to define this measure that we call association between a set A and the graph B. And basically, it's going to measure, just like the definition of the cut, the sum of all edges between nodes in A and nodes in B, all the graph. So this is the total connection, if you want, from nodes in A to the graph. Now that we have this, we can define a normalized cut rather than a cut. And basically, it's going to be the cut between A and B divided by normalizing it by the association between A and V, and the same cut between A and B divided by the association between B and V. So this is going to be the measure of dissociation, if you want, between clusters in the graph. And for the same price, we can also use this normalization to define a normal association within clusters. So I'm looking at A, and I'm defining, in the same way, association between A and A, which is just the sum of all edges within A, and the same thing for B, total weight edges within a group A, and I'm normalizing it using the same way. Yeah?
I am unclear as to why.
So wait a couple of slides, and I'll show some nice property of this, and maybe it will convince you. So far we defined two metrics, or two measures. One of them measures or quantified some global measure between A and B, two sets. And another one measures something that has to do with the association between the clusters. Now notice that we want to minimize this, or at least we think we want to minimize this, because this has something to do with how many edges, or how heavy are the edges that go between A and B. Normalized by the size, if you want, something that is related at least to the size. If all the similarities were the same number, it would be just the size. So it's a weighted size of A and weighted size of B. So the intuition is that this will avoid these cases of taking just one point. It will take a larger number of points, because then I'll have a larger number in the denominator. So this is something that I'd like to minimize. At the same time, if I'm looking at the association metric, this is something that I want to maximize, right? Because I want that if I split my set of points just to A and B, I want that A will be tight, and I want that B will be tight. So I want that the association metric between A and A is going to be large, and the same here. It's going to be large, right? This is the similarity within the cluster, and again, normalized relative to the size of the graph. So basically, these are the two metrics that we talked about at the beginning that we, in principle, we want to maximize the similarity within a cluster. We want to minimize similarity across clusters. And so far, we said that it's going to be difficult, that it is difficult to achieve both of them. So here we're going to do a little bit of algebra. We're going to start with the dissociation measure that we want to minimize. This is the normalized cut, which we've defined this way. Now, the cut between A and B can be written as the association between AV minus the association within A. Same thing here, cut between A and B. Now I'm writing it relative to B. Association between B and V minus the association of B with itself. And so this is 1. This is 1. So I'm getting 2 minus this metric, which is the internal association of A and B, normalized. Or the normalized association, which is the metric that we wanted to maximize. So what we've seen here is that we get this nice property where the stuff that we want to minimize is just 2 minus the stuff that we want to maximize, so we can achieve both of them together. This is the nice property of this algorithm, and this is the intuition that hopefully will lead to a good clustering algorithm. And in practice, it turns out that it is a pretty good clustering algorithm. Basically achieves simultaneously what we wanted to do. Of course, there are issues of how to compute this efficiently. The typical ways for doing it is using eigenvalue problems and eigenvalue algorithms. And it's a pretty good algorithm. Again, in practice, I think that in almost all cases, even though this used to be hot for a while, it's not clear that it's doing better than methods like k-means. If you know what you're doing in terms of devising good distance metrics, but it's a different method that has some interesting applications. Okay, to summarize what we've done, we talked about clustering, and I really gave you a very, very quick survey of what is being done with clustering. Talked about standard approaches, like k-means and agglomerative methods, and the relations to probabilistic modeling. Talked a little bit about graph theoretic methods. And really, there exists a lot of clustering algorithm in the literature. It's also still an active research. And the key issues are these two. I mean, one is how to learn good metrics, because in many applications, you still want to learn the metric. And the second one is, of course, scalability, because for large problems, you want to do other things. You don't necessarily want to be able to compare all pairs of points, even that would be too much, and issues like this. I included here a few slides that I will not get to about learning metrics, but I think this would be a good enough summary. Questions? Okay, so let's stop here. Next, on Thursday, my plan is to answer questions and kind of remind you what we've done during this semester. So please come prepared with questions. That's it. So see you Thursday.